Welcome to the 6th class in the Physics of Materials lecture series. In the last class we looked at the initial stages of how we would go about putting together a free electron theory for conduction in metallic systems. So we will continue with this discussion. What we saw last class was we compared, we took the idea that one of the models for a metal is that there are ionic cores, and then there are electrons that are freely running across the extent of that solid. So you have a block of metal, the electrons, the so called free electrons are free to run across the extent of that solid. So that is the picture that we have, and to the extent that those are free to run across the extent of that solid, we treat them almost as though they were behaving like molecules of a gas. Okay. So with this idea or this picture or this analogy between a gas and a solid, the intent is to see if there is a theory that we can use for gases which we are more familiar with and extend it to a solid. Okay. So a gas being a state where the atoms are free to run around and there is minimal interaction between the atoms or molecules of the gas is generally much easier to model. So much easier to write equations to describe the behavior of a gas. So and therefore it makes sense that at least our initial attempt to try and understand what is happening inside a solid starts off with something that we understand of a gas, which we extend to that of a solid. To the extent that the constituents within the solid have at least some resemblance to what in their behavior to what a gas does. Okay. We also did some calculations last class to see to what extent we are justified in making this analogy, to what extent we can make this connection between the behavior that we see in a gas and the behavior that we see amongst the electrons in a solid. The positive aspect that we noted was in favor of making this comparison was that depending on the crystal structure even up to 50% of the solid might be vacant. Okay. So I specifically pointed out to you that when you pick up a solid metallic object in your hand, it is not immediately apparent to you that 25% to 50% or even more, depending on the ionic radii and so on, even more can actually be vacant space. It does not look like that. It is a very solid continuous object that you have in your hand. Okay. It is just that that vacant space is so evenly dispersed across the extent of that solid that we do not perceive it like that when you pick it up in your hand. Okay. So but nevertheless, if you actually do the calculations, if you look at the atomic radii of those atoms present or their ionic radii, which would be which in this case may be smaller, and you just look at the total volume that is available, given that that is the crystal structure and there is a lattice parameter attached to that crystal structure, which we can experimentally verify using X-ray diffraction or other such techniques. We can experimentally verify that lattice parameter. If you take all that into account, we realize that anything like 50%, 25%, 50% or even higher could be vacant space within that solid. So therefore, given that there is such a large vacant space and the fact that the electron is such a tiny particle relative to a gas molecule, taking these two into account, it comes across to us that it is reasonable to treat it as though these were gas molecules, treat the electrons inside a solid as though they were gas molecules running freely across a very large volume. And from that perspective, it seems that it is reasonable to extend these gas laws to free electrons which are present within a solid. We also did some other calculation to compare the number density, so to speak, of particles or the particle density that is prevalent in a gas at STP to that which is prevalent in a solid, to the number of electrons that are the density of electrons present in a solid. We find that there is a 3 orders of magnitude difference in the particles, the number of particles that gas particles that are there per unit volume at STP, when you compare that with the number of electrons that are present per unit volume in a solid, in a metallic solid. So we took silver as an example and we came up with some numbers. So we find 3 orders of magnitude difference. In other words, there are, for every molecule that you find per unit volume in a gas, there are 1000 electrons that you find for the same unit volume inside a solid. So this is a huge difference, a 3 orders of magnitude difference is a very significant difference, and therefore there is reason from this perspective to be cautious on making such a jump in trying to make the connection between the behavior of a gas and the behavior of an electron gas in a solid. Okay. But we still believe that overall there is it is not far fetched to make this connection, it is not far fetched to try and make some equations out of it. So we treat and it is also relatively straightforward to do so, to write the equations down. So we just run through the process, we will put these equations down, we will see what we get in terms of electronic conductivity, we will see what we get in terms of thermal conductivity, and we will see how well this kind of a theory is able to predict experimental values in both cases, and also how well it is able to predict the relationship between thermal conductivity and electronic conductivity, because as we said in one of the earlier classes, in general we find that metallic systems which are also good conductors of electricity also happen to be good conductors of heat. So given all these things, we would like to see how well this theory is able to predict all of these, the electronic conductivity, the thermal conductivity and the relationship between them. Okay. So this is where we are headed with this analogy. What we will do today is we will review a few of the important results from the kinetic theory of gases, because those will be results that we will directly utilize in our calculations when it comes to electrons in a solid. So that is what we are going to do. So we will please remember, at this moment the discussion is pertaining to gases in a volume. Okay. So we will extend the result. So at the moment it is still a gas in a unit volume, in some volume. So now let us take a volume, we will take a box of side L, a cube of side L, and we will designate this as your positive x direction, and into the plane of the board will be the positive y, and the vertical direction would be z. Okay. So so we have this x y z coordinate system that we are using here, and we have let us just say that we have n moles of an ideal gas. Okay. We have n moles of an ideal gas inside this volume. So that is what we have, that is the system that we are working with. What we will do is we will start with one particular, we will say it is say an atom or molecule of this gas, and let us say it is moving with a velocity Vx in the x direction. Okay. So and we will say the molecules have mass m. Okay. So the momentum of this particle so this is the initial momentum of this particle. We will say that it goes and let us assume that it runs this is a cube of side L, so all sides are L, all the dimensions are L. I mean, this is just for our convenience, we start with something like this so that it we are able to get something out of the result. So we have a momentum mvx headed in the positive x direction. So this is what is the state for with respect to this particular molecule. So it let us say it collides with this this face out here, and then it bounces back, and we will assume that this is a large box and the collision is elastic. So it bounces back, momentum after collision so we will say this is final, this is initial, equals it will be back, it will be headed back after collision with with Vx in the opposite direction. So we will just call this minus Vx, is its velocity. So momentum is now minus mvx. Okay. So final momentum is this. So for the particle which has now bounced off of this surface, change in momentum with the final momentum minus the initial momentum minus mvx minus so it is minus mvx final momentum minus of the mvx which is the initial momentum. So this is simply minus 2 mvx. So for this particle which moved which had a component of velocity in the x direction vx, as it bounced off of the surface that is out here, the change in momentum for it is minus 2 mvx. So that is the result we have. So therefore the momentum that it has transferred to the front surface is the opposite of this. So this is the momentum that has changed for it. So the opposite change will, since momentum is conserved, the opposite would have occurred for the box. So the momentum transferred to this front face or to this face, that is not the front face, the side face, momentum transferred is plus 2 mvx. So that is the positive opposite of what happened to the particle is been transferred to this front of this box. So now we know the change in momentum. Okay, so we know change in momentum for the particle, which we know change in momentum for the box. So these are two things that we know. From here we would like to get some expression for force and then some expression for pressure. Okay, so force is rate of change of momentum. So we would like to know the rate at which this change in momentum is occurring. This is change in momentum, we would like to know the rate at which this is occurring. So if you go back to this picture here, we have a box of side L and velocity here is Vx. So once you have a collision here, for it to come back and collide at this surface once again, it has to travel all the way back here, make a collision with the face that is on this side and then come all the way back to the front to this face. Okay. So it has to travel L and it has to travel back L, that is basically what will happen before it can make a second collision with this surface, right. So it has to travel a distance to L, okay, and its velocity is Vx. So the time it will take to travel this distance so this is the time that it is going to take before the it collides again with the same surface, right. So it is transferring this momentum and then and the time interval over which it is doing this transfer is effectively this, because that is when the next transfer will occur. So therefore rate of change of momentum for the box okay. So 2 mvx by 2l by vx, so 2 will get cancelled. So this is equal to mvx square by l. Okay, so this is rate of change of momentum for the box as a result of this single particle repeatedly colliding with one surface of that box. Okay, so that is the rate of change of momentum of this box due to the particle that is moving with this velocity vx. Okay, and rate of change of momentum is effectively force. So force is defined as the rate of change of momentum. So force exerted by the particle repeatedly colliding with that surface is this expression mvx square by l. So this is for that specific particle. Okay, so if you had other particles, they may have different velocities, and so for each of those particles we would have to identify that specific velocity and use that specific velocity. For the particle that we are considering, it is this is the expression, of which m is fixed for all the particles in the system. All of them are the same kind of gas molecule. So m is the same for every particle you consider inside the box. L is also the same because that is the box, we do not have a different box, it is all the same. Only difference from particle to particle is the velocity. There is bound to be some distribution of velocities. So some particles may have higher Vx, some may have lower Vx, some may have the same Vx and so on. So you have variation here. So now total force, okay, total force exerted by all of the particles, on the same surface. Is this simply the sum of this expression for all of the particles, and as I said, m is the same, l is the same, only the v is going to change. So depending on the particle we will call it particle 1, particle 2, particle 3 and so on, and we will assume that there are a total of n particles there, capital N particles. So we basically have m vx1 square by L plus m vx2 square by L plus m vx3 square by L plus dot 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 all the particles okay. So this is what we have a sum of the m vx1 square by L plus m vx2 square by L plus m vx3 square by L plus all the other particles plus m vxn square by L. So this is the total force exerted by all the capital N particles that are present within the system. We already know that we started by saying that there are n moles of an ideal gas present inside. So therefore this n, if you have Avogadro number, this capital N is simply a small n times Avogadro number. So that is your total number of particles present. So we will write this as a summation here. So this is simply okay mvxi square by L. Now it is a bit cumbersome, so in fact we will actually even simplify this. So m and L are constant as I pointed out, so m and L are out. Okay, so m and L are constant, so they are already out. So we actually have sum of the squares of all of the velocities of all of the particles present in the system. So that is what we have here. In reality it is going to be cumbersome for you to actually know, in fact not cumbersome, it is just not practically feasible for you to actually know the velocity of every single particle present within the system. Okay. So therefore what we actually do is, if there is a way in which we can figure out an average velocity, okay, and we will assume that we know there is an average velocity. If you know the average velocity, then this sum is simply the average velocity times the total number of particles. So that is basically all it is. So that is the sum, okay, and this capital N, as I pointed out, is simply the number of moles times Avogadro number. Okay, so Na is Avogadro number, this is the number of moles, that is the total number of particles. This capital N is total number of particles present within the system. So therefore we have total force times the total number of particles, which is this Na, times the average of the squares of those velocities, and that is simply denoted by this notation here. Okay, so this notation simply means average of the squares of those velocities. Okay, so if vx1 square plus vx2 square plus vx3 square, like that up to vxn square divided by capital N. So that is therefore that would be the average squares of the average of the squares of the velocities. Okay, so that is what we are looking at. So this sum here has been replaced by the average times the total number. So that is basically all it is. Okay, so sum over all the particles has been changed to the average for all the particles times the total number of particles. So this is what we get for the total force. Now we would also recognize that we have only taken the x component into account. Okay, okay. So we have only discussed the x component. In general, if you look at the square of the modulus of the velocity, it is going to be Vx square plus Vy square plus Vz square. So a given particle could have a velocity some in arbitrary direction v, so it has an x component, a y component and a z component. So these three are there. So in general the actual velocity that you have, the square of the actual velocity will be Vx square plus Vy square plus Vz square, and in general if you take all the particles into account, as such there is no, since we do not have any specific preferred direction, okay, so there is no specific preferred direction, a particle could have equal probability that it has a certain velocity in the x direction or the y direction or z direction. So there is no preferred direction where it is likely to have higher velocity, okay. So in general we can treat that Vx square will be of the same magnitude as Vy square and also the same magnitude as Vz square. So in general since we are assuming equally random random directions, random velocities and so on, that there is no preferred direction, preferred orientation, preferred direction for higher velocity. In general these three will be of essentially the same magnitude. So therefore we could write Vx square, so this is the same as saying V square is equal to 3 Vx square. Assuming everything is random, this is the same as saying this, okay. So therefore we can write for a given particle, this is in general going to be the case, in general, okay, roughly it is going to be this is going to be the case. So therefore we can now, this is just the general velocity, we have now removed the components x, y and z are all equally probable, so that is this already accounts for all of them. So we are not looking only at the x direction, we have generalized the situation. Therefore now total force is simply m n n a okay. So we have m, the mass of the molecule, n is the number of moles present in that volume L cubed that we have been discussing, Na is the Avogadro number, n capital A here, Na is the Avogadro number. This average of the squares is essentially the mean of the squares, okay. So when we calculate root mean square velocity, that is the square root of this. So this is mean squares, mean of the squares, that is all it is, we have not taken the root here, mean of the squares is the value that we are interested in, so that is what we have here. So m n Avogadro number, mean of the squares 3 times the extent of that solid L, okay, of that box L. So this is the expression we have for total force, right. So now we have an expression for total force and we still have our original picture of a box of side L, so therefore a cube of side L. So from this we would like to come up with an expression for pressure. Pressure is simply pressure exerted on this face, for example, is simply the force exerted on this face by the area of that face. So we have pressure equals F by L square, and that is therefore equal to m n n a okay. We had 3L, now it becomes 3L cubed, so this is what we have, and L cubed as we can as you can imagine is simply the volume of this cube. Okay. So if we rearrange now, we have PV equals m n n a right. So we started out by looking at this cube, we have come up, we have tried to see what kind of change in momentum exists for a single particle, therefore tried to come up, therefore identified an expression for the change in momentum for the box, then converted that to a force exerted by that single particle on that box, and then a force based on all the particles, effect of all of the particles undergoing a similar change in momentum, generalized for the velocity in the system, and then we have come up with this situation there where you have PV equals mn Na V square by 3. Now based on our knowledge of the ideal gas laws, we see that based on how the ideal gas behaves, we have PV equals nRT. R is the gas constant per mole on a per mole basis, N is the number of moles, and T is the temperature of this of the system. So we have these two expressions. So clearly we can equate them since both of them are referring to the same ideal gas and the same expression we have on the left hand side. So therefore nRT or M N Na V square by 3 equals nRT. Okay, so we can cancel out n, and therefore we have M V square equals 3 RT by Na. Okay, so this is the expression we have mv square. This is mass of a single molecule. This is the square of the mean of the squares of velocities, 3 RT by Na. So this is what we get, and we have a definition for the Boltzmann's constant, which is simply the gas constant on a per molecule basis, which is since this gas constant is on a per mole basis and you have Na molecules per mole, so R by Na is the Boltzmann's constant, which is Kb. Okay, so therefore is 3 kBt. For us more than mv square, the quantity or the expression that is of use for us is half mv square, which is the kinetic energy of the system. Okay, so therefore we would like an expression for half mv square, which is simply half of this. So therefore okay, so we get this expression that half mv square, which is the translational kinetic energy of a molecule, translational kinetic energy of a molecule is 3 by 2 kBt. Okay, so this is a very useful expression, so we will make note of this. So this is a translational kinetic energy of a single molecule on average. Okay, on average for a single molecule, this is the translational kinetic energy. This relates to this Boltzmann's constant, which is the gas constant per unit on a per molecule basis, and this is the absolute temperature that we have here. Okay, so this is what we get. So this is one expression that we will find useful for our later purposes. We will extend this a little bit more. Right, so we have an expression for the translational kinetic energy of a single particle. So supposing you have we started off with a volume V equals L cube, right. Given that we now have an expression for the translational kinetic energy of a single molecule, supposing we have Nt okay, supposing you have Nt molecules per n subscript T molecules per unit volume. Okay, if in case you do this, then the translational kinetic energy associated with or the kinetic energy, total kinetic energy from all those molecules running around is simply Nt times 3 by 2 kBt. Okay, so therefore E equals 3 by 2 Nt kBt. Okay, so this is the energy, the kinetic energy, and therefore the energy held by those molecules per unit volume, because this is the number of molecules per unit volume. If you took some other number, then it would be on the volume on that basis. Okay, so on the volume corresponding to this. So this is energy per unit volume effectively. Now if you want the specific heat of this system on a per unit volume basis, we now have the energy on a per unit volume basis as a function of temperature. So therefore Cv is the differential of this with respect to T, and this is simply 3 by 2 Nt Kb. Okay, so Cv is simply 3 by 2 Nt Kb, fine. So this is the specific heat per unit volume associated with the system of all these molecules running around at that temperature T inside that box. Okay, so on a per unit volume basis we are able to come up with this, and so this is another useful expression for us. We just put it down here again, Cv equals 3 by 2 okay. So we have two important expressions. We have one for the translational kinetic energy, half mv square equals 3 by 2 kBt, and one for the specific heat at constant volume which is 3 by 2 Nt Kb. Okay, so this is what it is, and as I mentioned, this Nt is the number of molecules per unit volume. Now all of this discussion we have done keeping in the system that we have spoken about is an ideal gas system, and therefore the molecules present within that system are all the ideal gas molecules. Okay, so they are fairly massive, so you could have argon or something like that which is mimicking an ideal gas present within that box. We are and these are results that we have derived on the basis of the assumption that such a gas is occupying this volume. What we are headed towards is that we are going to take these results and apply it on a gas containing effectively a gas of electrons. Okay, so therefore what will happen in our system, the way our equations will change is that specifically this m, which we would normally associate as the mass of that molecule and therefore would be a very large mass in general, this m will now become the mass of an electron. Okay, so this equation, though we have derived it for a ideal gas, we are extrapolating it for the gas of electrons that we have in the metal. We are assuming that those are all ideal, I mean they are behaving close to that of an ideal gas molecule kind of behavior, and therefore the equation we will use will be the same, except that we will this m that we have here, we will now change from the mass of the molecule to the mass of the electron. These velocities will be the velocities of those electrons inside that solid object. Those electrons, as we said, are now free to run around across the extent of the solid. So whatever we associate as their velocity in any which manner that we can identify a velocity associated with those electrons, those velocities we will incorporate here. This Boltzmann constant, those are all universal constants, nothing is going to change. So this part of the equation is going to remain the same. Kb, this is the temperature at which that system is. So this is going to look exactly the same. This expression here is the specific heat at unit for unit volume, as I said. So if you take a solid, when you look at the specific heat of a solid as opposed to that of a gas, in a gas we are directly talking of those gas molecules. Okay, so when you raise the temperature of a gas, those gas molecules pick up that energy, they run around all around the place, their velocities go up and so on. So that is how the temperature of that solid, that is how it is able to exhibit a higher temperature, that gas, that container containing the gas. Now in a solid we actually have two things, we have especially in a metallic system, okay, we have those ionic cores which are present. Okay, so so that is definitely still present in the solid. In fact, when you pick up the solid, that is what you actually feel, that is that solid piece that you feel, all those ionic cores that are present. Then you also have this free electron gas that is running all around the system. Now when you raise the temperature of that solid, the energy is being absorbed by those electrons which are running across the extent of the solid, as well as those ionic cores. Okay, so together all of them are actually absorbing the energy. So it is not that it is absorbed only by the electrons or absorbed only by those ionic cores. In a metallic system we have a very distinct capability of distinctly identifying or at least distinctly associating our analysis with the free electron gas present there. So we will assume for the moment that there is a free electron gas, and with the free electron gas we have the ionic core. The temperature of the entire system is going up, so the ionic cores also absorb energy, the electrons also absorb energy. So when you talk of specific heat per unit volume, okay, you have to accept the fact that in that unit volume there are electrons as well as there are ionic cores, okay. So whereas the analysis that we have done so far has talked only about the ideal gas, and that behavior, that ideal gas behavior, we are extending only to the electrons, to those free electrons. We are not extending this behavior, we are not making a comparison of this behavior with the behavior of those ionic cores. In our picture the ionic cores are held in very rigid positions or relatively rigid positions in the form of a crystal structure or a lattice and so on, okay. So they are not free to run across the extent of the solid, largely they are stuck where they are stuck, but they do vibrate about their mean positions, okay. So we will look at that in greater detail, but we have to keep in mind that those ionic cores are not stationary, they vibrate about their mean positions. So one of the ways in which the solid absorbs energy as you raise the temperature of the solid is that the amplitude with which those ionic cores vibrate actually goes up, okay. So when you look at specific heat, what you are looking at is the amount of energy you have to provide to that solid for a unit increase in temperature. So that is basically what we are looking at, some unit increase in temperature, what is the total amount of energy you have to provide that system. So clearly if there is more than one mechanism which can absorb the energy, you have to provide energy to allow both those mechanisms to gain the equivalent amount of temperature, only then the temperature of the solid actually goes up, right. So when you talk of specific heat of a solid per unit volume, it is the specific heat of all of its constituents per unit volume. So it is the specific heat of electrons per unit volume plus the specific heat of the ionic cores per unit volume. Now in the expression that we have derived, we have focused only on the part of the solid that behaves like an ideal gas, which is the electrons. So this equation here, this Cv equals 3 by 2 Nt Kb will be something that we can extend only to those to that free electron cloud, to the free electron cloud. So we will simply in our notation we will simply call this Cv with a superscript E, indicating that the fact that this is specific heat at constant volume for the electrons, okay. So specific heat at constant volume for the electrons, or the electronic contribution to the specific heat at constant volume, if you wish to call it that. This is the electronic contribution to the specific heat at constant volume. The ionic cores also have a contribution to the specific heat at constant volume, which we are neglecting. So this is now the same expression 3 by 2 Nt Kb, okay. And in this, these are identical expressions except I have added the superscript E. Here so if you look at this original expression we derived for an ideal gas, we are extending that to the electronic cores present in the system. So this is specific heat at constant volume, electronic contribution to the specific heat at constant volume. The other thing is that this Nt is now the number of electrons, number of free electrons per unit volume, okay. So this Nt is now number of free electrons per unit volume. Okay. So Nt is now the number of free electrons per unit volume. This is again something you should pay attention to because the solid actually has a lot of electrons, okay. So when you have essentially given the atomic number of that solid, whatever is the atomic number, that many electrons are present per atom in that solid, okay. So that is a huge number of electrons, okay. So that is a very large number of electrons, of which only a small number, a very small number, which is equivalent, which is essentially equivalent to the valency of that atom, the most common valency that it adopts. So in the case of silver, for example, it is +1. Only 1 electron per silver atom is contributed to the free electron gas. Every atom in the silver metallic system. So you have a block of silver, in that every atom is contributing only 1 electron to that free electron gas, okay. So when you look at the number of free electrons per unit volume, it is only this one per atom that is getting counted, even though that atom actually has many other electrons which are all bound to that ionic core, okay, which stay with that ionic core, and therefore it is a large number of electrons per unit volume. For this calculation we are only looking at the number of free electrons per unit volume. So these are two distinctions that we should be very conscious of as we continue this analogy, as we continue this discussion, as we extend it from a gas to a solid. The first thing we have to be cautious about is that we are talking of electrons and not the ionic cores, and importantly that the ionic cores also make a very major contribution to the specific heat. In fact, if you at higher temperatures, the contributions from the ionic cores to the specific heat is way greater than what the electrons contribute to the specific heat. The electronic contribution to specific heat is visible only at very low temperatures, okay. So largely it gets swamped by the ionic contributions at the higher temperatures. So that is the number one point that we have to keep in mind. Number two point is the electronic contribution to the specific heat is also something that we are associating only with the free electrons in the system, not all the electrons in the system, okay. So these are two major issues that we have to keep in mind. So and therefore this equation, when you extend it to the electrons in the solid, we keep those two things in mind, that this is Nt is the total number of free electrons per unit volume, and this is of course the Boltzmann constant. So what we have done today is we have looked at the kinetic theory of gases and derived or refreshed in our minds some of the major results of this kinetic theory of gases. Specifically we have come up with an expression for the translational kinetic energy associated per molecule, and we have also come up with an expression for the specific heat at constant volume. We have done this for a ideal gas, and we have seen with what kind of precautions we can extend this to a solid, and therefore identified how those equations are subtly different when you actually talk in terms of what is occurring inside a solid, and the fact that these are going to now be associated with the electrons in that solid, right. So in our general scheme of things, when you look at what we did last class and what we have done today, we have now said that we will extend this ideal gas theory into a solid and predict its electronic conductivity, predict its thermal conductivity. So to do that we have to actually we will do those two in the next couple of classes, but as we do those derivations we will borrow the incorporate the ideal gas theory into those derivations, and specifically we will incorporate these two results that we have just seen here today. Both of these results will be incorporated into the derivations that we will make for the electronic conductivity as well as the ionic conductivity, I am sorry, electronic conductivity as well as the thermal conductivity. And as I mentioned, we recognize the fact that the general metallic systems which happen to be good conductors of electricity also happen to be good conductors of heat, okay. So it turns out that for all metallic systems there is a relationship, there is a ratio for the thermal conductivity to the electronic conductivity. So as I mentioned in one of our earliest classes, the whole purpose of creating a model is to understand the system, and the extent to which we have succeeded in the process, it depends on how well we are able to make every prediction, okay, or rather we make a prediction, how well does it match to what is actually experimentally observed. So when we make predictions for the electronic conductivity, and so when we come up with an expression for the electronic conductivity, we will look at the literature, and I will show you some values for electronic conductivity for common metallic systems, and we will see how well the number compares. This theory we are coming up with will depend on something very fundamental to the system. So we are talking of mass of electron, velocity of the electron and so on, which are all fundamental to the system. So from there we are going to actually come up with a value for electronic conductivity. Similarly we will also look at something very fundamental to the system and come up with a value for the thermal conductivity. Again we will look at the literature, we will see look at values for thermal conductivity which are commonly seen for various metallic systems, and we will see how well our theory has predicted that thermal conductivity. So these are two now independent predictions we have made. Even as an expression we will be able to take a ratio of the thermal conductivity to the electronic conductivity based on the expressions that we will derive, and therefore we will see what ratio we come up with, okay, and we will discuss this in the next class. So when we come up with a ratio, again there will be a value associated with that ratio, we will see how well that value matches with what is in the literature. So these are some things that we will do. In all these cases one of the issues that we have to keep in mind is in all these derivations we often make some approximations, right. So therefore in general our prediction needs to be looked at from the perspective of an order of magnitude, okay. So if you are in the right order of magnitude there is a good chance there is reason to believe that our general approach and the manner in which we have made this analysis is reasonable, okay. So we will not so even when I look at the electronic conductivity value and compare it with what is there in the literature, our intent is not to look at the exact specific value of what it is going to be, okay. So it is satisfactory to us if a metallic system has a certain order of magnitude of conductivity and say 10 power 7 Siemens per meter, and the prediction comes out to be roughly in that range. So this is the this order of magnitude issue is another thing that we wish to look at. And so when we do this we will also see that in some our intent is to see how well this model has predicted all the experimental data that we see. So not only will we see we will try and identify all the places where it actually does a good job in making the prediction. We will also try and see what are those specific instances where this kind of an approach of imposing ideal gas rules on the electrons inside a solid in which conditions does this approach actually fail. So what kind of experiments are giving you results where this kind of an approach is finding itself inadequate to give you an correct prediction. So that also gives us clues to where exactly this theory is weak, and on that basis we will now be able to modify and then try and see if there is a much more robust theory that we can think of that we can incorporate, okay. So this is the way in which we will gradually go from a theory of this sort to a more sophisticated theory. And as I mentioned also in one of our earlier classes that to the extent that the theory makes a prediction that is acceptable to us in a range of conditions, then within that range of conditions we can continue to use the theory. So for example as we go forward I will point out that there are reasons we will find that there are places where the theory that we are using is going to be successful and there are places where it is going to fail. Just the fact that it has failed in some cases does not mean that the whole theory is entirely useless to us. To the extent that we use it within its limitations, this theory is still acceptable to us. So that is the framework within which we need to look at each of these theories, right. So in our next class we will develop the electronic conductivity, and then the class after that thermal conductivity, and then we will look at the limitations and successes of this theory, and we will always keep this in mind that the failure does not mean it is utterly useless, because even the subsequent theories that we come up with will each independently have an additional level of success that they will attain, but still we will be able to look at experimental data and find places where those theories are also still not adequate enough. So we will have to go through several levels of sophistication before we find a theory which is actually quite comprehensive, which is actually doing a pretty good job of explaining several aspects associated with conductivity at room temperature or at a range of temperature for a wide range of materials, okay. So only when we reach that far do we get the confidence that our theory is sophisticated enough, that it is accounting for enough number of details, it is realistic enough that it is actually working, okay. So we will reach that stage, and at that stage we will have a satisfactory theory for the material system. We are now in our process of getting there, okay. So with this we will halt this class, and we will take up our discussion on electronic conductivity and how these equations can be incorporated into it in our next class. Thank you.